Okay, so today we're going to move into talking about vectors in 2 dimensions and 3 dimensions, and this is chapter 3 in your textbook. Now, as we talked about previously, indicating the direction of a vector in 1 dimension is pretty easy. We simply use the polarity to indicate the direction of the vector. If it's a positive vector and it's in the x direction, then it points to the right. If it's a vector that has a negative value, and it's pointing in the x direction, it points to the left. And the same sort of reasoning with up and down being positive and negative along the y direction. So one-dimensional vectors, the sign of the one dimension there is all that is needed to indicate the direction. But what if we have a vector such as vector r here, shown in this diagram, that's pointing between positive x and positive y? That is, it's pointing partially in a plus x direction, but also partially in a plus y direction. So here we see vector r, and I'm going to go ahead and label it in here a little darker in bold and put an arrow. And so this is vector r, which I will label vector r like that. Okay, so vector r here points, as you can tell, up and to the right. Okay, so if we call the amount that r is pointing in the x direction r sub x, and the amount that r is pointing in the y direction r sub y, then we can write the vector using its components r sub x and r sub y. For example, I could write this vector and say vector r, is a certain amount r sub x in the x direction, plus a certain amount r sub y pointing in the y direction. So here in this particular notation, this little x with a hat on it and this little y that has a hat on it are known as unit vectors. These are simply little symbols, okay, is the best way to think of them, little symbols that indicate which direction which component points, okay? Now many books will use an x, y, and a z to stand for the different dimensions on the axis. Your particular book, instead of using x, it uses an I to represent the direction of the component along the x-axis. Instead of using a y, it uses a j. And instead of using a z, it uses a k. So this ijk unit vector notation is very common. It's often it's used by many different textbook authors, and it's used in mathematics as well. And so in your particular book, the x will be replaced here with an I and the y with a j. But they're still unit vectors. They're still just little symbols that remind us of what direction each component points. Okay, and they are called unit vectors. They're just symbols that remind us of what direction r sub x and r sub y are pointing. So in other words, when I look at vector r, okay, and I consider how much it's pointing in the x direction, if I imagine like a light shining down from above, the amount that vector r is pointing in the x direction is like that, as I've shown there shaded in. And so that becomes my r sub x value. Okay, the amount that r is pointing in the y direction, if I shade that in, okay, that's the amount that vector r is pointing in the y direction. So the little x, the I and the j simply indicate to us which component is r sub x and which component is r sub y and which component is r sub x. Okay, so that's one way we can indicate the direction of a vector. So we don't usually draw these parts, the x, r sub x, and r sub y. We simply draw vector r, but we indicate its direction and its size all in one statement like this. Okay, we indicate its direction and its size with one statement like this, and this is called vector component form. So as we just mentioned, the I is just a unit vector or a symbol to remind us that r sub x is pointing along the x direction. And similarly, j with a little hat on it is simply a symbol to remind us that r sub y points along the y direction. They must be there because when numbers are placed in the positions of r sub x and r sub y, that's the only way we're going to be able to understand which is which. For example, if somebody told me the following vector a was equal to 3i plus 5j, then it's clear to me that 3 is the x component because it's attached there to the I, and 5 is the y component because it's attached there to the j. If it weren't for the I and the j being there, how could I tell? If they had simply written vector A is equal to 3 plus 5, I could never tell which was the x component and which was the y component. Again, if we were to ever deal with a three-dimensional vector that has a z direction, then we use the unit vector k to represent the z direction. So here we see a diagram, an attempt at a three-dimensional type of a sketch, showing that I points along the x direction, j points along the y direction, and k points along the z direction. And of course, these vectors would be at right angles to each other in our coordinate system. Now, just to make sure you're understanding this and this method of writing vectors in component form, okay, what I'd like you to do in this example is you've got a coordinate system shown there. If you want to sketch that onto your piece of paper in front of you, you can do that. And I want you to draw for me vector A, assuming that vector A is equal to 4i minus 2j. Okay, vector A is equal to 4i minus 2j. Draw that vector into a coordinate system like that is the one that's shown here on the screen, and see if you can get vector A sketched in there properly. So pause the video, sketch your vector A, and then continue to see how you did on that. Okay, so how did you do? Is this pretty much what you drew for vector A? Did you draw vector A pointing to the right and down such that it's 4 units to the right and 2 units down? If you did, you've got the hang of this. So component form, drawing vectors in component form is a pretty easy thing to do. Most students find it pretty intuitive. If you are following along in this, that's good. You have a good understanding of vectors already. One more simple try at this just to make sure you've got it. Draw for me vector B, which would be minus 4i minus 4j. So pause the video, sketch that, and then continue to see if you have it right. And hopefully what you drew was something like what is shown on the screen right now. If you did, you've got it right. So one thing that's clear, I hope that's clear to you now, is that we can always get the sign of our components correct by drawing the vector and then looking at the vector in the diagram. Okay? We don't need to let our calculator tell us the sign of the components. We're going to be right every single time by simply looking at our picture. And this is another reason diagrams and pictures are so important in physics. For example, in the diagram on the left, if you look at this diagram over here, vector r points in both a plus x and a plus y direction. Whereas the diagram on the right, vector r, which points up and to the left, points in a positive y, but a negative x direction. So we could always get the signs of our components right simply by looking at the picture. Again, looking at the one on the left, r sub x and r sub y would be negative in this case. And the signs of our components in this diagram on the right, we would have a positive x and a negative y. Okay, so we can always get the signs of our components correct by just observing our diagram and our picture and how the vector's pointing in our coordinate system. Now, one thing that I want to mention as we go further into this is that if you're a student who's in this course and you've already had quite a lot of vector math in the past, and you're very comfortable with vectors, you understand what a vector is, you can put vectors into component form, polar direct, polar angle form, you can add and subtract vectors, multiply vectors, you're just very, very comfortable and you have a method worked out. Please don't let me mess you up. Okay, there's no requirement that you do vectors the way I do them or the way that I'm going to show you here. But some of you might have been like me as a student, where when you first encountered vectors, they were a little confusing to you, and you maybe got some wrong answers and really didn't have a good method for how to, consistent method for how to handle them. What I found was that I found through kind of trial and error, if you will, I found that the following method, the method I'm going to teach you here in this class, was the method that I found gave me the highest percentage chance of right answers. In other words, I made fewer mistakes and understood the vectors better doing them the way I'm going to show you in this course. Okay, but again, so if you've struggled with vectors in the past or you've never learned them before, I'm going to teach you the way that I think will give you help you be successful. But if you already have an established understanding of vectors and you're very good at them, for example, I've had students that use the complex math notation on their calculator to do vectors. I don't want to mess you up. If you're getting right answers with vectors and you understand them, then just keep forging ahead with it. But for some of you, what you'll find is that I think if you adopt this method I'm going to show you, it will help you. It'll help you make less mistakes with vectors and understand them better. So as you just saw in that previous slide, one of the things we need to be able to do with vectors is change their form. We need to change them from one representation to another representation. And why we need to be able to do that will become clear here later on as we get further into this. But for right now, there's basically two different forms that we want to be able to represent vectors in. The one is the vector component form, which we've been discussing. The other, though, is the what I'll call the polar form, or I like to call it the magnitude direction form. Okay, it's basically where we tell you how big the vector is and what angle it's pointing at. Okay, so polar coordinate form is more the kind of the form of a vector that a meteorologist, if the meteorologist is going to tell you the velocity of the wind, they don't generally say, oh, the velocity of the wind today is 4 to the east plus 5 to the north, or something like that. They usually will say something like the winds are out of the northeast at 25 miles per hour. So they're basically telling you how strong the winds are, the velocity, the magnitude of the velocity, and then they use a description like, oh, they're out of the northeast, or 30 degrees south of west, or they use some kind of a direction coordinate system like on a compass heading to indicate to you what direction the winds are coming from. And so that's kind of our magnitude direction form for representing vectors. And we can completely represent a vector like that. I could tell you how fast a car was moving and the exact compass heading it was traveling at, and I've completely specified that car's velocity. On the other hand, in an XY type coordinate system or an XYZ type coordinate system, I could indicate the exact size and direction of that car as well by giving you the components, by telling you how much in the I direction, how much in the J direction, and how much in the Y direction it was moving. Okay, and so we got to be able to go back and forth between those two basic forms, the vector component form and the polar form. So case one here is where we have to change from the polar coordinate form or the magnitude direction form to the component form. Okay, and to do this, as you see on this slide right here, to do this, you have to already know. They are going to have told you, okay, the magnitude of vector r. That's part of telling me the polar coordinate form. And also, they're going to have to tell us some angle. They're going to have to tell us some angle where the vector's pointing. Now, what we need, or what we want, is we want the smallest angle, okay, which is going to be always less than 90 degrees, right? Smallest angle between the vector r and the x-axis. So if vector r, and the easiest way to figure out that angle, that smallest angle, which a lot of books will call the working angle or the reference angle. Okay, I've seen this terminology used in books, working angle. You might have had a math professor that used that terminology, or reference angle. This is the smallest angle between the vector and the x-axis. Okay, so if I put my pencil, right, if I take my pencil and I put it on vector r, and I just take the quickest route to the x-axis, like that, that's the working angle. Okay, and we usually use an angle, we usually use a Greek letter theta, the small Greek letter theta, to represent an unknown angle. So again, if I put my pencil on vector r and I take the quickest route to the x-axis, that's the angle I want. That's the smallest angle. So for example, I could put my pencil on vector r and I could come around to the x-axis that way, but that's the long way. We want to take the short route, the smallest angle. So the angle that we're talking about here, our reference angle, is always going to be between the vector and the x-axis, the shortest path or the smallest angle. Now, once we have those two things, once they've told us the size of vector r and they've told us the angle where we've determined, sometimes they don't even tell us this, but we can figure it out using our smarts. Once we have those two things, now we're able to start putting the vector into component form. Okay, but we have to have those two things first, or we don't know the vector we don't have the vector completely specified. So once they tell us these things, once we know those, now we're ready to start. And the way we do this is, you'll notice here in this yellow box at the bottom right part of the screen, the size of vector r, or the absolute value of vector r, or the x component of vector r, the absolute value of r sub x, the x component, is going to be equal to the size of vector r, right? Size of vector r times the cosine of that working angle or reference angle. Okay, the absolute value or the size of r sub y, the y component, is going to be equal to the size of vector r times the sine of that angle, that working angle. Okay, so again, these absolute value signs here that you see in these expressions are telling you that we're going to get a positive number. So using this system that I'm showing you here, you're going to plug in positive numbers for r, for the size of r. You're going to plug in angles that are less than 90 degrees. And when you crank through this, you're going to get positive numbers. We're going to get the size of the components. Okay, and the reason that we do this is because we can always look at our diagram, our sketch of the vector, to determine the signs of the components. We can always figure out whether they're plus or minus components by looking at our diagram. Okay, and so these equations here in this box at the bottom right of the screen are the equations we would use then to get the size of the components. Then we simply insert the sign, or we get the size of the components with the equations here, and then we insert the signs, right, whether they're plus or minus the components, using our own smarts. We don't let the calculator tell us that. We do that ourselves. So again, oftentimes one of the best ways to understand something is to see it done for you, or to practice it and see it demonstrated and then practice it. So what I have here is I have vector c, and I've told you that vector c is 10 units long, and I've drawn vector c into a diagram. And what I want us to work on here is how do we convert vector c then into vector component form. Right now I have vector c, I have it in magnitude direction form. They've given me some angles to indicate the direction, and they've told me how big vector c is. Vector c is 10 units long. Okay, I don't know what the units are. Maybe they're meters, centimeters, I don't know. But vector c is 10 units long, and it's pointing at angles like this that they've sketched into the diagram. Now, if you remember our working angle, if I put my pencil on vector c and I take the quickest route to the x-axis, that is the angle that we typically call theta. That's my working angle over here. Okay, and so that's the angle I want to use with this system. 30 degrees here is the angle between the vector and the y-axis. Okay, and for right now, we're not interested in that. We want the angle between the vector and the x-axis. So we just take the quickest route between those two, and that's the vector or the angle that we're interested in. So here our working angle is 60 degrees. And so now that we know that our working angle is 60 degrees, which we established right here, all we have to do now is follow the rules. We say, okay, vector c is 10 units long. That's how big vector c is. So the x component size for vector c is going to be 10, size of vector c, times the cosine of my working angle, which is 60 degrees, and I get 5. 10 times cosine of 60 degrees on my calculator, assuming I'm in degree mode. Okay, some calculators, when you start the calculator up, it will want you putting your angles in radians. You don't want to be in radian mode here. This is degrees, and so if you're in the proper mode on your calculator, cosine of 60 degrees times 10 is going to give you your 5. Okay, now we turn to the y direction and we say, okay, well, the y component size, that's why these absolute value signs are here, right? The y values, the y component size for vector c is the size of vector c, 10, times the sine of the working angle. And in this case, that's, of course, the sine of 60 degrees. So 10 times sine of 60 degrees gives me my 8.66. Now, as the last step, now that I know that the size of c sub x is 5 and the size of c sub y is 8.66, now I look at my diagram over here and I say, okay, well, what signs does vector c have? Well, obviously, it's going to have a negative x component, and it's going to have a positive y component. I can see that it's pointing over to the left and up. And so now when I go to write vector c, guess what I do? To write vector c, I simply take the vector, write it with the vector symbol over the top of it, right up here. Put my vector symbol. I say vector c is equal to -5 in the I direction plus 8.66 in the J direction. Remember, J stands for the Y direction and I stands for the X direction. So in this case, vector C points some to the left, -5 to the left, right, and positive 8.66 up in the positive Y direction. And that is how I write vector C. So what I've done in this example is converted from a polar coordinate form or a magnitude direction form that they gave us at the beginning of the problem like this. They gave us this picture and they told us this, and we have converted it now to vector component form. Okay? So that's one thing we want to be able to do with vectors. Now, again, I could solve a bunch of these for you, but the best way to get the hang of this is to do it yourself. So here's vector D. Vector D is 12 units long, and you have a diagram there showing you where vector D is pointing. And what I want you to do now is pause the video and use this method to write vector D in vector component form. So how did you do? Vector D, if we look at vector D here, vector D, you should have got vector D is about 7.22i plus 9.58j. And the way we did that was we found our working angle or our reference angle, and we also established how big vector D was. And then to get the size of the x component, we took the size of the vector times the cosine of the working angle. To get the size of the y component, we took the size of the vector times the sine of the working angle. Once we established the size of the components, then we simply look at the diagram and we determine what the signs are of the components. And in this case, they're both positive. This vector points to the right and upward, which are both in the positive direction. So we write vector D as positive 7.22i plus 9.58j. And one more time, let's have you try this one. Vector F is 10 newtons. Let's suppose that we give the units a name here, newtons, which is actually a unit of force, as we'll learn later in the course. Vector F is 10 newtons, and you have this diagram. It points 30 degrees. Sometimes we would call this 30 degrees south of east. Okay, sometimes we give directions of something's pointing. You know, we typically would use a north, south, east, west type coordinate system. And so sometimes people may indicate vector F here as 30 degrees below the x-axis or 30 degrees south, right, heading south of east. So the second term, when you use that type of terminology, if somebody says south of east, it's the second word that is where you start from. You start from the east over here, right? And you head south. The first word tells you the direction to head from there. So south of east would be like that, as shown with that arrow. Okay, so you know, sometimes if they use words to describe the direction, you've got to be able to interpret those words and get a diagram. But here we have vector F. It's 10 newtons, pointing 30 degrees below the x-axis, down and to the right, and I want you to convert that into vector component form. And I think that's probably enough for
so how did
this
you do?
lecture. That gives you some things to practice and work on.
Get your
Keep in mind that doing vectors, adding and subtracting vectors,
the x-axis,
manipulating vectors
our
is a
working
really
angle or
important part of
reference
this
angle.
course. It's a really important part of a
F
lot
was
of your
10
science and
newtons in
engineering
size,
courses.
10
So
times
you
cosine
want to get up
30
to
gave
speed
me
on this and be
8.66,
very proficient
10
at
times
vectors.
sine of 30 gave me 5,
And now looking at vector F, it points over to the right in the positive x direction, and it points down in the negative y direction. And so I make sure I put my signs in here, plus 8.66 minus 5. And what do I get? I get vector F is 8.66i minus 5j. If you've got that right, good job. So that was going from polar coordinate form or magnitude direction form into vector component form. Case 2 is the other way around. We want to be able to go from the component form to the polar coordinate form. And the reason for that is, what if my instrumentation, for example, to measure the velocity of the wind, what if it gave me the information, the sensors gave me the information in an IJK type of a format? I want to be able to get that into polar coordinate form or the magnitude direction form in order to explain to somebody what the vector is. So I've got to be able to go back and forth between these two forms. So let's practice going from the component form to the polar form. So to do this, the first thing we're going to need to know We cannot do it otherwise. We don't know the vector otherwise. Someone's going to have to tell us the size and the signs of the components. Okay? So we're going to have to know r sub x, r sub y, and if there's a third component, r sub z. Okay? Most of the time in this course, most of the work we do is in 2 dimensions, and of course, going into 3 dimensions isn't a whole lot harder. Okay? But we stick mostly with 2 dimensions. Okay? And so once I know the size and the signs of the different components, I can draw a sketch of what vector r is, right? I can always draw a sketch. To go from one form to another, I have to know the vector completely. So regardless of whether I'm doing case 1 or case 2, whether I'm going from component form to polar form or polar form to component form, it doesn't really matter. I'm going to have a picture of how my vector is pointing. Okay, I've got to know that. So knowing r sub x and r sub y, how do we get it into polar coordinate form? Well, the size of vector r, which remember, we can use double bars, double lines on both sides of the vector to indicate the magnitude of the vector, but more commonly what we do is we just remove the vector arrow from the top of the vector, and that stands for the magnitude of the vector. Okay, so again, either one of these forms right here is common for indicating the size of a vector or the magnitude of vector r. But the magnitude of vector r, to get that, I simply take the square root of the sum of its components squared. Now, if I had a third component, what if I had a third component? Well, vector r then would be equal to the square root of r sub x squared plus r sub y squared plus r sub z squared, right? I would just take that square root, and that would give me the size of vector r. So if I had if vector r had 3 components, okay, the rule is still the same here. I just extend it to 3 components, like that. Okay, right now we're just going to deal with 2-dimensional vectors, and so for right now, really all we need to deal with is our 2 dimensions here. So we're going to go ahead and erase that. And the size of vector r, would be the square root of the sum of the components squared. Now, even if this was a negative component, even if one of these had a negative value, when you square it, it goes positive. So the important thing here is you don't even have to worry about signs with this particular method. To get the size of vector r, you just take the size of r sub x, square it, size of r sub y, square it. If there's a z component, size of r sub z squared. Add them together, take the square root of the sum, and that's the size of your vector. Now, to get the working angle back, the reference angle or working angle back, okay, then what you do is you take the inverse tangent of the size of vector r sub y, or component r sub y, over the size of component r sub x. Okay, so you take the magnitude or size of r sub y, the positive value, absolute value of r sub y, over the absolute value of r sub x, and you take the inverse tangent of that fraction, and that will give you the working angle back. And of course, the best way to get good at this and understand it even better, of course, is to see it demonstrated and then to practice it yourself. So here we see vector v, which is shown as 5 meters per second I minus 6 meters per second j. So maybe v here is a velocity vector for the wind or something like that. So vector v is 5 meters per second I minus 6 meters per second j, where of course meters per second is simply our units that the speed, the velocity vector here is in. And we want to convert that. We want to convert that to a magnitude direction form. We want to be able to describe to somebody where this vector v is pointing and how big vector v is altogether. Okay, in other words, how fast is that velocity altogether, and what angle is that wind blowing at, for example? Okay, so one of the things we got to be able to do is figure this out, and we want to take a look at this. And here's how we would do that. Again, the size of the x component is 5. The size of the y component is 6. Even though the y component is negative 6, when we square it, it's not going to matter. So simply to get the size of the vector, I take the 5, I square it, I take the 6, I square it, I add it together, and then I take the square root, and I get the size of the vector. The vector here, v, has a size of 7.81, and that will be in the same units that the components were in. If the components were in meters per second, then my final answer for the magnitude is in meters per second. Now, what angle does vector v point? Well, remember, to get the working angle back, the smallest angle between the vector and the x-axis, I take the size of the y component, which is 6, and I divide by the size of the x component, or the I component, which is 5. So I take the y component over the x component, or the j over the I get 6 over 5 in this case, and when I take the inverse tangent of 6 over 5, when I take the inverse tangent of that fraction, if I'm in degree mode, my calculator will return an angle of 50.2 degrees. So now when I look at my diagram, and I say, well, can I draw vector v, right? When we started class today, we were drawing some vectors using component form. Well, if I were to draw vector v here, 5i minus 6j, I could sketch that in. I could rough that in here and say, well, that's about 5 over to the right and about 6 down here to the negative j direction. So vector v is going to point somewhere down this direction. I'm going to be able to sketch vector v into a coordinate system, at least rough it out, from the description of the component form that I had at the beginning of the problem. So now I have my diagram, and if I put my pencil on vector v and I take my quickest route to the x-axis, of course that's my working angle. And in this particular case, the working angle, we were told, is 50.2 degrees. So theta here is 50.2 degrees. Okay? In other words, I could fill that in and say theta is 52 or 50.2 degrees. That's what it is. So now I've got the size of the vector, right? And I've got the angle it points at in my coordinate system here. And now I can finish this statement at the bottom, and I could say to somebody, hey, vector v has a magnitude of 7.8 meters per second, right? That's how fast the wind's blowing. And it's pointing at an angle of 50.2 degrees south of east, right? So in other words, the second letter, or the second direction, of course, is where you start from, and the first word tells you the direction you're heading from there. So I start in the east, right, which is over on the right side. If you don't know your north, south, east, and west, it's good to establish that if you don't know that at this point. All right, and so if I start at the east over here and I go 50.2 degrees south of that, that's the direction that the angle, or the direction that this vector points. Okay, so we've got a way that we can verbally describe it here, like shown here in the box at the bottom. We've got a way that we can pictorially represent the vector, and we've got its size here figured out as well. So we've gone successfully from the vector component form to the magnitude direction form, and that's the other thing we need to be able to do. And of course, the only way to get good at this is to practice it yourself. And so at this point, you will pause the video, and I want you to convert vector d, which is minus 4i plus 6j. I want you to convert that vector into magnitude direction form, okay, and then fill in the statement at the bottom of this slide. So pause the video and see if you can do this. And hopefully, if you did this right, you got an answer that's very similar to what I show here, that vector d is 7.21 units long, and it's the working angle here, which is the vector between, or the angle between the vector and the x-axis, shortest angle, smallest angle between the vector and the x-axis, is 56.3 degrees. And so completing our statement at the bottom, I would say vector d has a magnitude of 7.21 degrees, or I'm sorry, has a magnitude of 7.21 units, and points 56.3 degrees north of west. So I would start in the westward direction, and I would head north and go 56.3 degrees up off of the west axis. And of course, that tells me that my angle theta here is 56.3 degrees, and I've completely specified vector d. Now, going from vector component form to polar coordinate form, and from polar coordinate form back to vector component form, this is very, very important, and you should practice it as many times as you need to get very comfortable with that process. The other thing I want to mention is that officially polar coordinate form, mathematicians always measure angles up off of the positive x-axis, and they come around counterclockwise. So typically speaking, if I had a vector that was pointing down and to the left, like I'm showing here in this diagram, okay, the mathematician that's using the polar coordinate system would typically come up off the positive x-axis here and come around counterclockwise and measure that angle. So we're doing things the way I just taught you to do vectors, right? You would find the working angle, which is this one right there. Maybe I should highlight it a different color. Let me get some blue. So you would find this angle here, right? And if somebody said, give me the polar angle, then the polar angle I would have to add in this case 180 degrees on, because starting at positive x-axis around here would be 180 degrees, and so then I would add on the working angle that I found. So again, to be completely clear, polar coordinate form, the polar angle here, okay, would actually be the one that I showed there, coming around the counterclockwise direction from the positive x-axis. Now, on occasion, I don't think it's considered legitimate or that common, but sometimes mathematicians will use a negative polar angle. They'll come around clockwise from the x-axis, and they would call that a negative angle. But again, they generally come off the positive x-axis and go around counterclockwise, and that's the positive polar angle. If you come off the positive x-axis going clockwise, that's what they call the negative polar angle. All right, but typically we're dealing with the working angle. So you can see it's important to be able to communicate. If a homework problem says, what's the polar angle for the vector, you need to figure out this angle. And so you would figure out your working angle and then add on your 180 degrees to figure that out. Okay, if they don't specify, then of course if you have a drawing on a test or something and you say that's theta, and hey, theta is 30 degrees, that's completely fine to me, because it's clear from your diagram and from your note over here that you know what that angle is. But if it says give your answer in polar coordinate form, what would I answer in this case? If theta was actually 30 degrees over here, if I found that as my working angle, then my polar angle here that I would answer would be 180 plus 30, or 210 degrees. So I did just want to clarify that, and really that's one of the reasons I like to call it magnitude direction form, because polar coordinate form always assumes you're going to give the polar angle for the vector, and sometimes we like to just give the angle between the vector and one of our dimensions like west, north, south, or east. And so magnitude direction form, I think, kind of covers all of that. Okay? Now, one of the reasons you might be thinking, okay, so we've been doing all this work now on these vectors and converting them, but what's the purpose of that? Since there's two different ways to indicate a vector, why do I need two different ways? Again, the reason for that is because when we go to do mathematical operations with vectors, and what I mean by that is, adding and subtracting vectors, or multiplying vectors, dividing vectors, so on and so forth. When we go to do mathematical operations with vectors, typically it's easier to do when they're in vector component form. So for manipulating vectors mathematically, component form is a wonderful form to have them in. Okay. On the other hand, to communicate with people, oftentimes the magnitude direction form is the more comfortable and meaningful way to communicate with people. Like I said, if your weather forecaster started giving you wind velocities in X, Y, Z coordinates, or I, J, K units, you would be very confused. People are used to getting the direction that something's going and how fast it's going kind of together, like, okay, the car was traveling 100 miles per hour, 20 degrees east of north, or something like that. That is the way that most people like to communicate, but the IJK, the component form, is much better for doing mathematics with vectors, and so we're going to see that as we continue here. Now we're starting to run short on time here in this particular lecture, so we're probably just going to talk about adding and subtracting vectors today, and then we'll get into the multiplying and dividing vectors and so forth on the next lecture. Okay, so how do we add and subtract vectors? Well, this is pretty cool. It's pretty easy. Okay, adding and subtracting vectors is pretty easy. The first thing you do is get each vector into component form. Okay, once you get it into component form, then you add up the individual components and you get the resultant vector. Okay, it's that simple. So now this slide shows you kind of the technicalities of the adding and subtracting vectors. Actually, it's much easier than it looks on this slide. But if vector r was equal to a plus b, right? If vector r was equal to the sum of vectors a plus b, obviously vector a is equal to a sub xi plus a sub yj plus a sub zk. Okay, so there's vector a written. Vector b would be equal to b sub xi plus b sub yj plus b sub z k. Okay? And so adding the vectors together simply becomes a process of adding together the x components. I would have a sub x plus b sub x becomes my r sub x. A sub y plus b sub y becomes my r sub y, and a sub z plus b sub z becomes my r sub z. Okay, I simply add up the I components. That becomes the I component for my summation vector, or my resultant vector. If I add up the y components, that becomes the y component for my resultant vector, which is the sum of the vectors. If I add up my z components, that becomes the z component for my resultant vector. Okay, so actually adding vectors together is pretty easy. You just stack them on top of one another like I did here, right? And then you just do a little bit of elementary school math, adding up the columns. Right? It's that simple. Subtracting vectors, same sort of thing. If I wanted to subtract vector b from vector a, I would take the x component of vector a, subtract the x component for b. To get the y component, I would take the y component of vector a, subtract the y component of vector b. To get the z component of my subtraction vector there, d, I would take the z component of vector a and subtract off the z component of vector b. Okay, so it's a pretty straightforward process, and I think if we show it in the next slide, it'll even become more clear, because on this slide I have it set up to be more kind of visual. And so here we have, in this slide, we have vector c, we have vector b, right? Those are the vectors that somebody gave us. And so vector b, if you notice, is 4 units I plus 1 unit j, and vector c is 1 unit I plus 3 units j. Right? That's the vectors, and they're sketched in here, C and B, right? Now, if I go to add vector B and vector C, what do? I simply add up their I components, and I get the I component of vector B plus C. If I want to add the Y components together, I get the Y component of vector B plus C. So vector B plus C here is simply 4 plus 1, or 5I, and 1 plus 3, or 4j. 5I plus 4j. If I sketch it into the diagram, vector b plus c ends up right here. Okay, and you notice it's a combination of those two vectors. Now, what about subtracting vector c from vector b? Well, b minus c means I would take 4 minus 1, and I would get 3i, and I would take 1 minus 3, and I would get minus 2. In other words, you're simply stacking the vectors up and then doing the math on them. So 4 minus 1 gives me 3. 1 minus 3 gives me negative 2. And so vector b minus vector c simply becomes 3i minus 2j. And of course, if I sketch that in, 3i minus 2j, there's vector b minus c right there. Okay? So hopefully that makes sense. Once you see it visualized like that, you realize you're just stacking the vectors up and adding the columns is what you're doing. So let's try to pull this all together here. Let's try to add vector F1, shown in this diagram, to vector F2. In other words, I want to know the resultant force. I want to know what the answer is to vector F1 plus vector F2. That's what I want to know. I want to know that sum of these two vectors, F1 and F2, shown in this diagram. So again, what we have to do, you have to first convert vector F1 here into component form, get vector F2 in component form, and then you simply stack them on top of each other and add them up and see what you get. So again, if you want to give this a try on your own first and then look at the answer, you can pause the video at this point. If you want to just forge ahead and see how that's done, you can stick with me here and we'll flip the slide. Okay, so how did we do this? Well, first of all, we took vector F1 and we put it into component form. How did we do that? We got the size of vector F1. Vector F1, we were told, was 20 newtons. That's the strength of the vector. And we also got the working angle for vector F1, which is, in this case, 37 degrees. So the size of the x component of vector F1 we found as the size of the vector. Right? We found the size of the vector, 20, times the cosine of the working angle, and we got the size of the x component for vector F1. Then we took the size of the vector times the sine of the working angle, and we get the size of the y component for vector f1. Now looking at vector f1, we realize vector f1 is pointing up and to the right. It has both a plus x and a plus y direction. And so vector f1 was then written as 15.97i plus 12.04j. Now to get the vector f2 into component form, vector f2 has a size of 10 newtons, and we don't even really have to do any trigonometry here because we can see vector f2 is pointing entirely in the minus y direction. And so therefore I can simply say vector f2 is 0i, it points none in the left and right direction, 0i minus 10j. And then I write that vector down, and I have vector f1 and I have vector f2. I stack them on top of one another, add up the I components to get the x component for the, or the I component for the sum. I add up the j components to get the sum, and that's the j component of the sum of the two vectors. So 15.97 plus 0 gave me my 15.97 for my I component, positive. 12.04 minus 10 gave me my positive 2.04 for my y component. So vector f1 plus vector f2 is 15.97i plus 2.04 newtons j. And if I were to sketch that into the problem, guess what? It's going to point mostly to the right here, mostly to the right. Okay? A little bit up, a lot to the right. So technically, this resultant vector is pointing just slightly above the x-axis there, like that. Okay?